Hey everyone, in this video let's take a look at question 572, subtree of another tree on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question we are given the roots of two binary trees, root and subroot, and we want to return true if there is a subtree of root with the same structure and node values of subroot, and false otherwise. A subtree of a binary tree is a tree that consists of a node in tree and all of its node descendants. The tree could also be considered a subtree of itself. What exactly is that saying? So basically here you can see that we have our root, here we have our subtree basically, and we want to check if this subtree somehow exists inside of root. So we can see here that this subtree here actually exists right over here. We can see that the nodes are the same, children are also the same. What about in this case? Well, in this case we have a 4, 1, and 2 here, and similarly we have a 4, 1, and 2 here, but notice how here 2 is connected to a 0 here. So in that case, the subtree does not match exactly. The children on this hand are different than the children on this hand. You can see here basically that if the children were to match, then you can kind of think of this subtree as it'll be like a leaf, right? Like there won't be like anything underneath. So it has to match like that exactly. And then that's basically the question, right? So first of all, even before we get into this question, what do we know? Well, we know that root and subroot are optional, right? So we'll have some cases where possibly root is provided and subroot is not provided. So we can go ahead and take care of that. But otherwise, like, what's a way in which we might go about doing this question? Well, because if you think about it, like one thing we need to do is we definitely need to like go through root and subroot, right? We definitely need to do that. So one way that I'm kind of thinking that this is possible is we could maybe like go ahead and we start off at 3. So we just start off on the left hand side, we just start off at this root tree here. And for every node that we go through, maybe in like a DFS called in order, traverse, or pre-order, it doesn't matter. But basically every single node that we go through here, we go ahead and we cache that information inside of a hash map. And then what can we do? Well, we can do the same thing for subroot, cache that information in subroot. And then basically we can check like if there's any common node values, right? If there's any common node values, then we can go ahead and compare those trees to make sure they're the same. And we might have actually done a similar question to this one, which I believe we called, it might have been called same tree. But essentially same tree, what happens in same tree is that if I go ahead, open it over here, the same tree. In same tree, essentially what we're doing is we're given two binary trees and we want to return if they have the same structure or not. And I did this here. I will just copy and paste the code over here because we'll be using it. But essentially, that's what we might want to use in this problem. Now, with this first approach, it does work, but you might notice that we're storing a lot of stuff inside of a hash map, right? And if the tree is very big, you can see that the number of nodes actually like would be like 2,000. So it's not really that big, but you can see that's probably not the best solution here because we're storing all of the nodes in a hash map. So what's another way in which we can do this? Well, if you think about this, right, like how about we traverse these trees together? So instead of traversing root and then subroot separately, what if we traverse them together? So let's see how that kind of might play out. So let me go here and I'll paste this inside of the paint here. Okay, so let's say we traverse the two trees together. So maybe this is my, and a little bit right here. Okay, so let's say, what is the thing I'm looking for? Let me just do brush, right? So let's say this is where I'm starting off on root. This is where I'm starting off on subroot. Now, what do we notice about these two nodes? Well, we notice that they're different, right? Now, what if they weren't different? What conclusion could we make if these two nodes weren't different? Well, if they weren't different, then it's possible that they are the same tree, right? So maybe what we can do is if the nodes are not different, then I can go ahead and I can basically determine if this entire tree here and this entire tree here are the same tree. How can we do that? Well, we have our helper function to do that, right? We've done a question before where we can determine if two trees are the same. So we can maybe use that. Now, what about if it isn't the same? Well, if it isn't the same, then remember what we're doing, right? We want to essentially find if subtree here, like if this is a subtree inside of this. So given that we have that information, would it make sense for us to kind of move this pointer? Would it make sense for us to move this pointer down? Or would it make sense for us to move this pointer down, right? And if you really think about it, what we want to do here is we want to determine whether this subtree here is part of this main tree here. So if we go ahead and move this pointer down, right? If we go ahead and move this pointer down, then I no longer have access to this 4 here. So even if I arrive at a 4 here, I can't basically say that the trees are the same because I don't have access to this 4 over here anymore. But otherwise, if I can maybe move this pointer down to a 4, well, then I can check, okay, so maybe is this subtree here now, is this subtree equivalent to this one? And we can see that the 4s match, and then we can actually see that the trees themselves also match. In this case, we would return true. Otherwise, maybe this is not the case. So then what we can do is we can check the left-hand side or the right-hand side. And then we can check if maybe this part here matches with this part over here. But you can see what I'm doing. I'm basically not moving this subroot pointer. All I'm doing is I'm moving this root pointer. If they don't match, and if they do match, then I'm actually going ahead and comparing to see if it's the same tree or not. So let's maybe take a look at that approach, and that actually turns out to be the best approach here. So let's maybe take a look at how we can write the code for that one. Okay, so what can we do? Well, first of all, we need to go through both of the trees together, right? So we can do something like return self.helper, pass in both the root and the subroot. Okay, now I'll define my helper, root, and the subroot. Now, what are some base cases we need to consider? Well, it's possible that root is none, subroot may also be none, right? So if both of them are none, we can do if not root and not subroot, then we can just return true here, right? Because basically, like, there's nothing to do in this case. Okay, what about the case where like one of them is none but the other one isn't? Well, in this case, like, we can't have a subtree, right? Because one of the other trees is none, so it doesn't really make sense in this case. So we can do something like if not root or not subroot. This basically checks like if one of them is none but the other one isn't none. If this is the case, then we can return false. Okay, so now what do we have? Well, now we know that we have a tree such that both of the roots exist, right? The root exists and the subroot exist. Okay, now if root.value is equal to subroot.value, then what? Well, if these two values are the same, then all I need to check is that the trees themselves are the same, right? This is the exact same thing we would have done in our first approach. We would have found like intersecting nodes and then just verified that those trees are the same. So here we can actually just go ahead and do that, but we do it as part of our DFS call. We don't need to store it extra in like our hash map or anything. What I can do here is if these two root values are the same and they're actually the same tree, and I'll pass in the root and the subroot, then I can go ahead and return true, right? So again, what I'm doing in this case is that if I arrive over here, so let me go ahead and move this pointer. Let's say my pointer is over here. I notice that this and this are the same. So now I'm going to compare if these two trees downstream are the same, right? Because it's possible maybe something like here's like a 5, right? In which case the answer would be false. They wouldn't be the same. But in this case, the answer would be true. Okay, so let's go ahead and do that. So we already have that condition here. Now we have to handle the case where the values are not the same, right? The values are not the same. Initially, when we start off, we are at the 3 here and we're at the 4 here. So what do I need to do? Well, we already argued that we don't want to move the subroot. So we need to check this left-hand side. Maybe that's same as the subtree, or maybe the right-hand side is same as the subtree. So we can go ahead and do a recursive call here. So we can do return self.helper. Here we will look at the left-hand side of root, and maybe that is somehow, maybe that embeds subroot somehow, or maybe the right-hand side embeds subroot somehow. And so that's what we have here. So this is our helper function. The only thing we need to do now is code our subtree. And now here's actually the solution for subtree, but I'll go ahead and I already have a video for this one, but I'll just go ahead and explain it here while I'm doing it quickly. So same tree, what do we have? Well, we have 2 nodes, right? And similarly, we have a couple of the same conditions, right? So first of all, if one of the root exists, but if none of the root exist, then we know that it has to be the same subtree. If one of the root exists, but the other one doesn't, then we know that it's not the same subtree. Maybe the values themselves are not the same. So in this case, if the values themselves are not the same, then it's not a subtree. But otherwise, if we pass all of these conditions here, then basically what I want to check is if the left-hand side matches the left-hand side of subroot and the right-hand side matches the right-hand side of subroot. And if both of these return true, then I know that my children are the same. We already established that the root is the same, but if the children are the same, then we know that the entire tree is the same. Then what I can do here is I can just do return same tree, or self.sametree, root.left, subroot.left, and the right hand side child is also the same. Got right, subroot, got right. And that's basically this question. So now let's go ahead and run the code, run our test cases. Okay, and we arrive at false. So let me see where I messed up here. So root, subroot. So if not root and not subroot, that's correct. This is also correct. Dot val and same tree. Okay, so here, root dot subroot. So that's also correct. And then root dot left subroot, root dot right subroot. So maybe I messed up in the same tree somewhere. So if not root and not subroot, then this is true. If not root or not subroot, this is false. If root dot val does not equal subroot dot val, that is my problem. Let's go ahead and run our sample test cases again. They pass. Let's go ahead and submit. And awesome. So we arrive at the solution. What is the time here? Well, if you think about this, what we're doing is that for every single node in the root tree here, we want to compare it like with the subroot, right? So what's going to basically happen is if I go ahead and I start off back over here, so then this node here, if it's not potentially the same, right? If it's not potentially the same, if 3 does not equal 4, then I'm going to compare 4 with 4. If that's not the same, then I'm going to compare 5 with 4. Maybe downstream, I compare 1 with 4, 2 with 4, etc. So you can notice here that like for every item in the root, I'm going to be comparing it to the subroot here. So it's like if you think about this in terms of like a for loop, right? It's kind of like a n squared type operation. But really here, we want to know like the size of this thing, this tree over here. Maybe we can just call that m. We can say it has m nodes, right? Maybe it's written here. It's not. But let's just say this tree has m nodes. This tree has n nodes. But then the time here would be like m times n, right? Because I need to compare every node of this with the subtree, the subroot every single time. Okay, so that's our space. That's our time complexity. What about our space complexity? Well, if you think about this, like our space complexity, we need to go through this tree here, and then we also need to go through this tree here. But notice how we are not always like doing that, right? Like for example, like we can often just, if we arrive at our solution here, then we can just go ahead and we recurse back and we have our answer. So if you think about this, at the worst case, really, all I'm really doing is I'm going through this tree and then I'm going through this tree. So in that sense, the recursion stack wouldn't ever exceed m plus n, right? It wouldn't ever exceed m plus n. It's not like we would have like m times n number of recursive calls in any sort of iteration or any sort of like call. So the maximum would be m plus n in terms of how many recursive calls we would actually do. So that would be the time and space. Time is m times n, space is m plus n. Okay, thanks for watching.